Hey everyone, now we're going to take a dive into the second part of this unit. Now that we know how to name covalent compounds and organic compounds, that special kind of covalent compound, we are now going to take a look at representing covalent compounds. When we talked about ionic compounds, we really just talked about which atoms were part of the cation and which atoms were part of the anion. But we never really got into what is really there in that chemical if we were to look at it on the molecular level. Well, now we're going to do that. We are actually going to imagine that we could see inside of our covalent compounds on the molecular level, and by looking closely at them, then we could notice the shape that our molecules take. And this is actually a really important part of understanding chemicals. If you think back to biology, do you remember learning about the enzyme substrate complex? And every enzyme has a specific substrate and they have to fit together like a lock and a key. So you have something that's one shape fitting into something else that's a similar shape so that those two things can fit together and do what they need to do biologically. Well, that will bring us right back to this study of how the atoms in covalent compounds are arranged in space. The way that they're arranged in space will affect something like an enzyme substrate pair, and it will also enable us to understand things like the special qualities that water has. So water will have that sort of layer on top, that tension on the surface, because of the shape of the water molecules. And when we talk about cohesive forces and adhesive forces, it again ties back into understanding the shape of water molecules. So let's take a look at some important vocabulary that we're going to need to keep in mind. First, remember that covalent bonds are the sharing of pairs of electrons between two nonmetal atoms, and the electrons that are shared are the valence electrons. And so if you remember what we said about valence electrons, these are the electrons in the outermost energy level of our atoms. And so remember, we can have up to 7 energy levels in our atoms that contain electrons. The valence electrons are on the outside. They're on the outside of our atoms, so if we, for example, represent two atoms by just some spheres, as these atoms approach one another, remember the whole goal of bonding is so that those atoms become energetically stable. And they do that by either exchanging electrons or sharing electrons. And those outermost valence electrons are the electrons that will come into contact with one another first. So the valence electrons are responsible for our chemical bonding. We are going to represent the shapes of our molecules with something called Lewis dot structures. And basically, Lewis dot structures show us all atoms of our covalent molecule. And will also show us where all valence electrons are located for each atom of the molecule. And another really important concept that we've talked about is the octet rule. And so now our octet rule is really, really going to become important. We're going to look at it all the time now. And the octet rule basically tells us that most nonmetals, and I'm specifically focusing on nonmetals here. We could actually also talk about the octet rule for metal atoms, but since we're doing covalent compounds, I'm going to focus on nonmetals. Most nonmetals want 8 valence electrons to become energetically stable. And a very important exception to that is hydrogen, and hydrogen wants only 2 valence electrons to become stable. And remember that that number, or those numbers, 8 and 2, are based on the electron configurations of noble gases. Most noble gases have 8 valence electrons, which is what makes them very energetically stable, which is why they don't bond. And we have one exception in the noble gases, which is helium. Helium will only have 2 valence electrons and be stable. Hydrogen, element number 1, is very close to helium, element number 2. So if hydrogen just gets 2 valence electrons, it will become stable like helium. All right, so let's take a look at what we're doing here. I'm just going to draw out some Lewis structures for you. The first one we have is H2. So this is made of 2 hydrogen atoms. And if I think about my hydrogen atoms and the number of electrons that they have, the number of valence electrons that is, that means I have 1 valence electron for each hydrogen atom. So if these hydrogens bump into each other, then they each have 1, they each want 2 electrons to become like the closest noble gas, which is helium. And so this hydrogen atom will put its electron toward making a shared pair of electrons. And this hydrogen does the same thing. And so what we end up with is our 2 hydrogen atoms with 2 electrons between them. And these 2 electrons are the shared electrons. They belong to both hydrogen atoms at the same time. And so now we would say, okay, this hydrogen atom now has its 2 electrons that it wants, so it is energetically stable. And also this hydrogen atom also has its 2 electrons that it wants, and so it is energetically stable. The last thing we will do with our Lewis structures is everywhere that we have a shared pair of electrons, we're going to replace those dots with just a line. And so our Lewis structure for this molecule made of 2 hydrogen atoms is 2 H's with a line between them. Now let's look at chlorine. If we look at chlorine, it is in column 17, and we know that atoms in column 17 have 7 valence electrons each. And so again, I'm drawing out my valence electrons. Now take a look at how I'm doing this. This is actually going to be a good system that we want you to use when drawing your Lewis structures. When you're drawing out these electrons, you can put pairs around the element symbol. So 2 here, 2 here, 2 here, and then 1 there. So notice that my pairs are at the points of a compass, north, south, east, which doesn't have a pair, it just has 1, and then west also has a pair. Same thing over here, 2 electrons north, 2 south, 2 east, and then 1 on the west. Keep your atoms' electrons like that at the points of a compass to keep things organized and making sense. If you get sloppy about drawing your Lewis structures, it can get pretty confusing. So try to stay as organized as you can. So this chlorine atom has 7 electrons, and this chlorine atom also has 7. If they each donate an electron to become a shared pair of electrons, then everybody will be happy. This chlorine on the right-hand side has all of these electrons. Remember, the shared electrons belong to both atoms. So now this chlorine has 8 electrons, and our chlorine on the left also now has 2, 4, 6, 8 valence electrons. And so it is also happy. And so what we end up with now is our 2 chlorine atoms with 1 bond in between them. And so we're going to change that bond to a line. Remember, in a Lewis dot structure, a line represents 2 electrons. And then we have these guys, which are called lone pairs of electrons, which finish out our Lewis structures. So 2, 4, 6, 8 electrons, 2, 4, 6, 8 electrons. So there are the basics of Lewis structures. All right, now let's take a look at these instructions. I know this looks like a lot of information, and it is, and at first you're going to have to read this carefully every time you do a Lewis structure, but you will get used to it over time, and you won't have to look at this list as much. So here are our steps for drawing Lewis structures. 1, count the total number of valence electrons that should be in your structure. 2, choose the central atom. The central atom in your structure is going to be the element that needs to get the most electrons to complete its octet. In other words, it needs to find electrons and lots of them in order to have an octet. And then we can also choose the central atom sometimes, actually lots of times, by looking at the element that there is only one of. Now, sometimes there are some exceptions there, but lots of times this second rule works here. Step 3, we're going to attach all other atoms, which we're going to call the outer atoms, to the central atom by drawing lines between the central atom and the outer atoms. And remember that line is a covalent bond and represents 2 electrons. Step 4, use the rest of the electrons to create pairs that complete the octet of the outer atoms. Remember, the great majority of atoms will have 8 valence electrons when they're done bonding, and I put a note here to remind you that hydrogen is an exception to that. It will only bond once to have a pair of electrons. And lastly, number 5, when all the electrons are used up, be sure that all atoms obey the octet rule, and if they don't, then you need to adjust the electrons by creating multiple bonds. So let's hop right into this. An example Lewis dot structure, PCl3. When you go through this procedure, the first thing I tell students to do is make a list of how many valence electrons you have from your elements. So phosphorus, being in column 15, has 5 valence electrons. Each chlorine has 7 valence electrons. Now remember, though, that there are 3 chlorine atoms total. So when we add up our total number of valence electrons, we get 5 from phosphorus, and then we get 3 times 7, which makes 21 total electrons from our 3 chlorine atoms. Now we're going to add these up. 5 plus 21 is 26 total valence electrons. So when I'm done making my Lewis structure, I should see 26 valence electrons. All right, which atom is going to go in the center? Our phosphorus needs the most electrons. It only has 5 valence electrons. It needs 3. Each chlorine has 7. Each chlorine only needs 1 valence electron. So phosphorus will become our central atom of our molecule. Then we're going to draw a line from our central atom to each of the outer atoms. So notice I haven't done any counting or anything yet. All I've done is chosen my central atom and then said, all right, this one's in the center, everything else has to be bonded to it. And so I have drawn a line from that atom to the outer atoms. Now everything is connected, and now I have to start counting. Remember that this is our total number of valence electrons. So think of this like a bank account, or if you're at a store and you have $10 and you have to keep subtracting the things that you're going to buy to make sure you have enough money to buy everything that you want. All right, similar concept here. 26 valence electrons is all we got. So far, we have 3 lines in our structure. So that's 2, 4, 6 valence electrons that are used up, which means we now have 20 left. Our next rule tells us to take those other electrons and start putting them in pairs around the outer atoms first. And we want to make everything have an octet, remember? So as I am placing these electrons, I see that if I put 3 lone pairs here, I will have 2 bonded electrons, and then 4, 6, 8. So then my chlorine will have a total of 8 electrons, which is what it wants. This chlorine, 2, 4, 6, 8 electrons. This chlorine, 2, 4, 6, 8 electrons. Remember, stick them at the points of a compass, north, south, east, west. Now, every chlorine has 8 valence electrons. Yay! Now let's see, is there anything that doesn't have the correct number of valence electrons? Yes, of course, it's our phosphorus. Phosphorus has only 2, 4, 6 electrons. So I had 26 to use. I've used 8, plus 8 more is 16, plus 8 more is 24. That means I have 2 valence electrons left. I'm going to take those and put them as a lone pair on my central atom, my phosphorus atom. And there we go. Now phosphorus has 8, chlorine 8, chlorine 8, chlorine 8, and there is a total of 26 valence electrons. So this is a good Lewis structure. Let's take a look at our next one. For silicon, we see it is in column 14, so it has 4 valence electrons. And then we have 4 bromine atoms, each with 7 valence electrons. So that means 4 electrons here. 4 times 7 is 28 electrons here. When we add those together, we see that this Lewis structure will have a total of 32 valence electrons. So what needs the most electrons? Silicon. Silicon has just 4, so it needs 4 more. Each bromine needs only 1 valence electron, so they won't go in the middle, but silicon will. Now we're going to draw a bond from our central atom to each outer atom because they have to be bonded to that central atom. And so far we've used 2, 4, 6, 8 valence electrons. Now take a look at this. Silicon, right now, it's done bonding. It has 4 bonded pairs of electrons on it. So actually, this is a good sign because we don't need to worry about silicon and its number of electrons anymore. But our bromines, however, each only have 2 electrons. So we've used 8 total. 32 minus 8 is 24. Now we're going to start putting those other electrons in lone pairs around our bromines. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've used 32 electrons. Each bromine has 8 in the form of 1 bonded pair and 3 lone pairs, and my silicon has 4 bonded pairs, so it has its 8 electrons. We haven't used any more or less than our 32 that we needed to use, so this is a good Lewis structure. Okay, a couple more here before we're done. So first we're going to take a look. We will take a look at this, which is an oxygen molecule. Oxygen, being in column 16, has 6 valence electrons, but there are 2 of them here. And so we will multiply 2 times 6, which means a total of 12 valence electrons. How do we pick our central atom? All we have are 2 oxygen atoms. So the only thing we can do with our 2 oxygen atoms is bond them to one another. So there we go. We've used 2 electrons. We have 10 left. So we're going to place them as lone pairs. 2, 4, 6, 8, 10. That's it. I have run out of electrons. You have to count as you go along. And sometimes when you're counting, you're going to run into this situation. You should have 12 in the structure. 2, 4, 6, 8, 10, 12. That's it. You don't have any more electrons. And the problem here is that even though this oxygen has an octet, this oxygen only has 6 valence electrons. And so in a case like this, you cannot add any additional electrons. That's it. Those 12 electrons are all that you have to use. So what we're going to do is we're going to take 2 electrons from this oxygen atom, and we are going to do something that you have seen before in biology class. Now remember, I didn't just magically create 2 electrons. I took 2 electrons away from here, and I'm going to move them into here. And so I'm going to make a double bond between my oxygens. So a little earlier when I mentioned using multiple bonds, this is an example of a multiple bond. So this oxygen now has 2, 4, 6, 8 electrons. This oxygen has 2, 4, 6, 8 electrons. And my total number of electrons in my structure is 2, 4, 6, 8, 10, 12. All right, now that you see that you can use multiple bonds, be careful. Just because you can doesn't mean that you should. Always try to make your Lewis structures with single bonds first. Nature is simple. If molecules can form with single bonds, then they will form with single bonds and not be any more complicated than that. So try single bonds first. If you can't get single bonds to work, then you can use double bonds or even triple bonds. So we'll take a look at that in a moment. All right, our next molecule, we have 6 valence electrons for sulfur. We have 2 oxygen atoms times 6 valence electrons, which means 12. 6 and 12 is 18 total valence electrons. All right, now what's going to go in the middle of this molecule? Each of these kinds of atoms needs an equal amount of electrons. They all need 2 more. When you come to a case like this, pick the atom for which there's only one of them in the structure. And so that means sulfur in this case. So I'm going to put that sulfur in there. And I'm going to make a double bond from sulfur to each oxygen. And then I'm going to place the rest of the electrons. So I'd like you guys to pause the video, try this structure, and see if you can figure out what works to make this a good molecule. All right, guys, hopefully you realized that this is the correct Lewis dot structure for our molecule. We have 18 total valence electrons, and everybody needs 8. So 2, 4, 6, 8, 2, 4, 6, 8, and 2, 4, 6, 8. If we count up our total electrons, we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So we need 1 double bond in this molecule in order for everybody to have the octet that they want. All right, our last 2 examples. So here we go. N2, we will start here. And I actually want you guys to pause the video and see what you can do with N2. See if you can get the correct Lewis structure. And then come back and check. Okay, guys and gals, for this Lewis structure, we have 2 nitrogen atoms, which means 10 total valence electrons. So I've started with my 2 nitrogens here, and I've put a bond between them because we know they have to be bonded. And everybody wants 8. I have 10 electrons to work with. So 2, 4, 6, 8, 10. What the heck? That's my 10 electrons. How am I going to make this work? This nitrogen over here is looking good, but this nitrogen now only has 4 valence electrons. So we're going to do what we did before. We're going to take 2 away, and we're going to move those 2 that were here into the middle so that each of our nitrogen atoms has a double bond. And so then that gives us a total of 2, 4, 6, 8 electrons there. But still, this nitrogen only has 2, 4, 6 valence electrons. So I'm going to have to do it again. Take another pair of electrons away. Remember, you cannot add electrons. You can only move them. So I took a pair from here, and I'm going to put it between my nitrogens. Now I have a triple bond. That's the maximum number of bonds I can have between atoms. So let's see if this works. 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons, and then 10 total. And so this is a good Lewis structure. So again, a triple bond is the highest number of bonds we can have between 2 atoms. Start with single. If single doesn't work, try double. If double won't work, then try triple. All right, there's one more molecule there for you guys to try. Give it a shot, and then after you've tried it, come back and check your answer. Okay, guys, when you finished your Lewis structure, you should have 10 total valence electrons, 2, 4, 6, 8, 10. You have to have a triple bond here between, I wrote sulfur instead of Si, there we go. You have to have a triple bond there between silicon and phosphorus. It's the only way this structure will work. Remember, hydrogen only bonds once and then it's done. So just one bond there. And then silicon has 2, 4, 6, 8 electrons. Phosphorus has 2, 4, 6, 8 electrons. And so that is a correct Lewis structure.